and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star one on your phone to ask a question. I would like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time. I will now turn today's call over to Laura Bleacher. Thank you. You may begin.
Hello, everyone. I'm Laura Bleacher from NASA's Office of Communications, and I'm very excited to have you joining us today. We have an incredible panel of experts that are ready to answer your questions about science investigations launching aboard Northrop Grumman's 19th commercial resupply mission to the International Space Station for NASA. NASA and Northrop Grumman are targeting Tuesday, August 1st at 8:31 p.m. Eastern Time for the launch of the company's Cygnus cargo spacecraft on an Antares rocket from NASA's Wallops Flight Facility in Virginia. Here to talk with us about some of the research launching aboard the Cygnus are Heidi Paris, Associate Program Scientist for the International Space Station at NASA's Johnson Space Center in Houston, who will provide an overview of the research and technology aboard the Cygnus spacecraft. Catherine Toon, Integration Manager for Exploration, Environmental Control, and Life Support for the International Space Station at NASA Johnson, who will speak on Exploration Potable Water Dispenser. Dr. David Urban, Branch Chief at NASA's Glenn Research Center in Cleveland and Principal Investigator for Sapphire 6. Dr. Shane Hegarty, Chief Scientific Officer and Co-founder of Axonus Therapeutics Incorporated and Principal Investigator for Neuronics. Dr. Lasse Clausen, Professor of Plasma and Space Physics, University of Oslo, Norway, who will speak on multi-needle Longmire probe. And Tsutomu Yamanaka, Principal Investigator at IHI Corporation and Principal Investigator for iSpace SA. Each of our guests will give a quick overview of their research, and then we'll open the line so that media may ask questions before we move to the next speaker. If we have time at the very end, we'll take additional questions. Your phones are on mute now, and to get into the question queue, you can press star one at any time. We'll call on you, and the operator will open your mic so you can ask your question. And we please ask that you stick to one question at a time. You may re-enter the queue with a second question, which we will get to if time allows. Members of the public may also ask questions on social media using hashtag AskNASA. A replay of the teleconference will be made available on the NASA Videos YouTube channel. To start off, we'll hear from Heidi Paris, Associate Program Scientist for the International Space Station. Heidi joined NASA in 2006 after graduating from Purdue University with a Bachelor of Science in Aeronautics and Astronautics Engineering. Since joining the Research Integration Office in 2018, she's been focused on enabling high-quality scientific research to be performed aboard the space station. Over to you, Heidi.
All right. Thank you, Laura. And thank you to everybody for joining into the call today. I'm very excited to hear from our team of researchers and scientists today. The International Space Station is perhaps the most unique science laboratory in the universe. It enables scientists from around the world to really redefine the boundaries of their discipline by imagining what might be possible if you could take gravity out of the equation. It also has the ability to host research from every major scientific discipline side by side. So we have, microbiology next to fluid physics, around the corner from technology demonstrations, with earth science right outside the window. So the ISS really does have something for everyone. And the overarching goal of ISS research is to bring direct benefits to humanity. Now, in order to keep our existing scientific studies going and also to pave the way for new research, we rely heavily on cargo resupply vehicles, including the very versatile Northrop Grumman Cygnus vehicles. So this NG-19 spacecraft is going to be sending up the science and hardware to support approximately 40 different scientific studies, as well as facilities. And we're very fortunate to have the extremely talented group of scientists and engineers behind 5 of those investigations with us today. So I'm very much looking forward to hearing from them. To me, one of the really exciting aspects of the science on this flight is that it's a very diverse set of experiments. So we have, these life-sized, human-sized technology demonstrations, and we also have biology that is small enough to fit into a bread box. We have investigations flying as part of a larger series of studies, and then there are also brand new ideas that nobody has ever tested in space before. This flight is also going beyond the strictly technical with an investigation that is mixing art and space in order to inspire the next generation of explorers and creators. And all of these investigations really have the potential to make a big impact on not only life on Earth, but also our ability to explore further into space. In addition to the science that the researchers on this telecon will discuss, we also have a couple of important upgrades to existing ISS science capabilities that I just wanted to mention. First, an investigation called the Flow Boiling Condensate Experiment, or FBCE. It will be getting a new module to enable the study of heat transfer. This module, called the Condensation Module and Heat Transfer System, or CMHT, may be able to provide an improved understanding of the distribution and the flow of heat inside a system, which could enhance the mechanisms that protect astronauts from both extreme hot and the extreme cold temperatures in space. Second, the Cold Atom Lab, also called CAL, is going to be getting an upgrade that will give scientists more data in a wider variety of experimental conditions. So CAL is quite literally the coolest place in the universe. It cools atoms to within 1/1000th of a degree above absolute zero in order to study the fundamental behavior of particles and atoms. It's a field called quantum science, and this new module, which is appropriately dubbed the Quantum Observer, is an upgrade to the heart of this facility, and it will enable 5 independent research teams to continue to make discoveries in this groundbreaking field. Now, if you'd like more information about any of the experiments you'll hear about today, or any of the over 3,000 different experiments that have been performed on board the International Space Station over its lifetime, I encourage you to visit the ISS Research and Technology webpage at nasa.gov/ISS-science. You can also follow us on Twitter at ISS_research for updates on current research as it's being performed, which is also really interesting to get plugged into. Also, we are looking forward to the ISS R&D conference, Research and Development Conference, coming up in a couple of weeks, the week of July 31st. And this is really an opportunity for the entire ISS research community to come together to discuss results from recent ISS research, as well as how to best harness the power of the ISS platform to advance the R&D challenges that we face now, as well as in the future. You can find more information about this event at issconference.org. So I am excited to hear from our research team now, so let's get to that. Back to you, Laura.
Great, thank you, Heidi. Next, we'll hear from Catherine Toon, Principal Investigator for the Exploration Potable Water Dispenser. Catherine is the International Space Station Program Exploration, Environmental Control, and Life Support Integration Manager, and began her career at NASA in 2007. She has a Bachelor of Science in Biomedical Engineering from Texas A&M and a Master of Science in Engineering from the University of Texas. Over to you, Catherine.
Awesome, thank you so much. And yeah, definitely thank you for having me. I'm real excited to share with everybody about the Exploration Potable Water Dispenser today. High level, this new piece of hardware isn't quite new to station. We currently have our existing potable water dispenser on ISS that has served the crew well for many years, since 2008. What makes our new Exploration Potable Water Dispenser different is we've upgraded it entirely. So we've gathered all the lessons learned from how it's used with the crew, and also added some new technology that is available to us now since 2008 that is just exciting to give the crew some extra rehydration and drinking capability, of course, with the ever-growing crew complement on station. So this is a piece of hardware that was funded out of the ISS Program Office in a somewhat smaller group that's dedicated to look at life support systems for upgrades for exploration purposes, fixing things that need to be fixed to enable exploration, but also give us some extra capability for when we do long duration space flight. This exploration PWD is the latest set. I'm coming on NG19 that's improving systems with exploration in mind. Key things that this will also enable us to do, other than just many of the upgrades, if anybody has questions on, but is demonstrating UV LED technology, which is our point-of-use sterilization method prior to crew conception, which we haven't demonstrated in our water systems as of today, and this will be the first time to do that. Also, exploration PWD will enable our ability to go into dormancy, which means water stagnation within the system, which is usually a system no-no. And we're going to be able to demonstrate that we can go into dormancy and out, which is definitely a key component for exploration for the future, knowing that's going to be a reality for us. So we're real excited about this. I'm happy to answer any questions if anybody has any for me.
Great, thank you. We'll now take questions for Catherine. Again, please press *1 to be entered into the queue. And so, Catherine, can you talk a little bit about how this new hardware, the lessons that you have to learn from it, and how it will benefit future space exploration?
Yeah, absolutely. Yeah, so for what we are going to be able to learn and about this water system, rehydration capability on station, as I said, we do have our existing unit, the potable water dispenser, but that unit didn't have any, because of the time it was delivered and trying to make it as, simple and robust as possible, we didn't add any ground telemetry or data to that unit. For exploration PWD that we're sending, it's outfitted with all sorts of sensors and the capability for ground to do direct commanding to valves, and also just simply to check system health status and learn from the components that we've really never been able to learn from before, and how they perform in microgravity. Another thing we're going to be able to enable, like I said earlier, is this idea of system dormancy is kind of a, for lack of better words, a scary thing on station. We really actively try to keep water moving through all the systems to prevent microbial growth, biofilm growth, and when you go into system dormancy, it kind of asks for questions. But PWD will be delivered also with some bypass hardware, which allows the system to go into like a smooth wall tubing configuration, which will allow us to flush the system better, and again, hopefully be able to pull it out of what we call dormancy and recover the system for crew use. So there's just, and of course, just many other details about it that we've learned from crew feedback, as far as interface and the buttons on the unit and how it can work better for them. So it's really an exciting upgrade, upgrade, with, like I said, when we ever grow our crew complement, more crew on station, not having a line at the at the one water dispenser food rehydration station, I know the crew will be excited about.
Now we'll hear from Dr. David Urban, Principal Investigator for Sapphire 6. Dr. Urban has worked with NASA for 32 years with a focus on low-gravity combustion and spacecraft fire safety. Together with the Sapphire team and international collaborators, he has developed the Sapphire series of experiments which seek to improve our understanding of the impact of a fire on the habitability of a spacecraft. Dr. Urban?
Good morning, everyone. Spacecraft fire safety remains a catastrophic concern for human spaceflight. NASA and other space agencies take extreme care to reduce the risk and potential impact of a fire, but this risk can never be reduced to zero. So whereas on Earth, every inhabitable structure has been subject to full-scale fire testing, be it ships, planes, buildings, mines, submarines, etc. Prior to Sapphire, this had not been done for a spacecraft, and the challenge has always been the risk of presence of fire and the presence of a crew. So the Cygnus cargo vehicles offered a perfect solution, a habitable vehicle with no occupants. So using these vehicles, we've conducted progressively more challenging experiments over the Sapphire series, seeking to address several objectives. Specifically, what really is the behavior of a low-gravity fire of practical size? Does it different from what we can scale from our prior experiments, which when we've been doing them in other facilities, always been limited to the order of an index card in size. And so specifically, how fast will a fire grow and spread in a low-gravity spacecraft? And then what is the impact of this fire on the habitability of the spacecraft? And how long does the crew have to deal with the problem? How much does it raise the pressure and temperature of the spacecraft? And then, importantly, can we successfully model the vehicle impact to predict behavior in future spacecraft? So Sapphire experiments were designed to address these objectives by looking at both the details of the fire itself and its impact on the overall spacecraft. We look at the fire behavior in what we call the Sapphire flow unit, which uses the largest possible stowage unit at the far end of the away from the hatch. And inside this flow unit, we have an instrumented duct with 4 different samples of materials that are about 40 centimeters wide and 18 to 15 centimeters long, depending on the material. And we burn each of these in succession to measure the flame spread or growth rate to better understand the practical fire behavior. Meanwhile, the exhaust from this flow unit, the heat and smoke, exits the unit and flows throughout the spacecraft, which we've instrumented with temperature and carbon dioxide sensors. In addition, at the far end of the spacecraft, near the hatch, we have what we call the far-field unit, which contains more sensors and a smoke scrubbing system to test smoke post-fire cleanup technologies. But using the combination of these sensors, we can get a better understanding of the transport of the spacecraft and use that as a test for our models. So previous Sapphire experiments have shown that terrestrial experience of smoke inhalation being generally more threatening than the heat of the fire also applies in low gravity. We've also seen that typical spacecraft can tolerate a small to medium fire long enough for the crew to respond and put it out. And we've also notably demonstrated that in low gravity, fires can exhibit a behavior we see in 1G, which we call deep-seated fire behavior, where the initial extinguishment extinguishes the flame and it can reignite if not adequately cooled by the extinguishment process. So that adds additional challenges for extinction for future conditions. And Sapphire 6 will look further at these issues by examining the flame behavior in even higher oxygen concentrations close to those planned for lunar habitats. And I'm open for questions.
Thank you. We'll now take questions. You can use *1 to enter into the question queue. And while we're waiting, I wanted to ask a little bit more about, I know that, doing these Sapphire experiments in microgravity is really important for helping us understand crew habitability. But, what type of complementary ground investigations are you also doing?
We have a combination of ground and flight, but on the ground we're doing a lot of steps of modeling, simulations of the Sapphire runs, and doing corresponding tests with the materials in 1G and in partial G on the aircraft, the aircraft, and also looking at the transport of the smoke materials in similar volumes in 1G.
Great, thank you. We'll now take a question from the phone. Let's go to Bill Harwood from CBS News.
Yes, thank you very much. What's the biggest surprise you guys have found in all of these experiments? I'm trying to visualize a flame in space and how it might propagate down a wire or whatever. And I know you're saying it's a little bit slower, crew has time to deal with it, but what's the biggest surprise or the biggest lesson learned so far in this thing as you scale up these experiments? Thanks.
I guess as we scaled up, we did sort of demonstrate what we anticipated for a thinner fuel, that it will achieve steady spread, which you won't see in 1G. That if you burn something upward in 1G, the growth accelerates over time. But what we did surprise us was the deep-seated fire phenomena, where an well-heated piece of thermoplastic, i.e. plexiglass, didn't extinguish as fast as we anticipated, and in fact survived quite a long period and flow off and then reignited. So when we reactivated the flow, so that was so the existence and challenges of extinguishing something after it's burned for a substantial period of time was the big surprise. And
Thanks. We have another question on the phone. We'll go to Mark Carreau from Aviation Week and Space Technology.
Yes, thank you. It is Mark Carreau from Aviation Week and Space Technology. Can you give us some examples of how the data that you've gathered so far are being applied to future human spacecraft development? Is it flowing into the design and production strategies? And if you could also tell us how long Cygnus will be docked, and then I know it has to undock before you can do your experiments.
For the second half, I'm not sure of the timeline anymore. It's usually a couple of months before they undock, and because they need plenty of time to fill it full of trash before they undock. But we're sort of on the receiving end of that. It's immaterial to us as long as they, let us know when they're undocking. But as far as the flow into the system, we are doing a lot of modeling of the results from Sapphire to use that to predict the impact of the fire on the spacecraft. At this point, the impact is most the review cycle of existing spacecraft, but looking forward, the flow analysis and the is being considered in the selection of particularly smoke detector design systems, and is affecting the choice of how you design extinguishing systems for a spacecraft, how long you have to maintain the extinguishing concentration. So that is where it's flowing in on the, mostly at this point on commercial spacecraft that are using these results.
Thank you.
And this is Heidi Paris. Just to chime in, the current plan has NG19 unberthing on October 30th, so that's about a roughly 90-day dock duration.
Thank you. We'll now take a question from Elizabeth Howe from space.com.
Hi, thanks for finding time for us today. I was curious about what kinds of lessons learned that you implemented from anywhere through Sapphires 1 through 5 that are helping to design to make Sapphire 6 a little bit more robust or a little bit more effective in terms of its experiment. Thank you.
So the, I guess the two lessons learned is one is in order to do Sapphire, we wanted to raise the oxygen concentration of the spacecraft to get near the exploration atmospheres, and we bring bottles of compressed oxygen, which we add to the vehicle after Northrop Grumman vents it down to a lower pressure. We've found that we need to that there's more free volume amongst the materials than we estimated, so we have to work harder to get them as much trash as possible. So we've previously were asking they keep some standoffs, 4 standoffs clear for us. Now we're reduced that to 2 to allow them to pack more material in the vehicle to reduce the volume lower enough that we can bring the oxygen concentration up to the desired levels. And otherwise, we are adapting our extinguishment strategy for the materials to make sure they have plenty of time to go out. Conduct the remaining tests. We had on Sapphire 4, notably, we had a little too vigorous a flame on the second sample, which interfered with subsequent tests.
Thank you. One other question from Clay Leopard from WEWS in Cleveland, Ohio.
Hey, Dr. Urban. This is Clay Lepard from the ABC affiliate in Cleveland. You mentioned how Sapphire has involved progressively more challenging experiments, and you just elaborated a little bit on how this one compares to those of the past. How much further would you like to see these experiments and these tests go?
Well, beyond Sapphire, right? This is the end of the current series. I think the big question for us next would be to try to do something similar in lunar gravity, but that'll be in the future. I mean, the lunar gravity situation is also challenging because there's an enhanced flammability at reduced gravity compared to 1G or even 0G. So that is the next big area of interest. But beyond that, we would be interested in looking at more complex geometries of samples, more realistic configurations in low gravity to continue our study for all future spacecraft.
And one final question in the queue is from Will Robinson-Smith of Spaceflight Now.
Yes, hello. Thank you, Dr. Urban, for taking the question. Just to build off of your last response, given that the lunar environment is sort of the next area of study that you'd like to take this, would that be something that would potentially happen on Gateway, Orion, or are you thinking something that would be on the surface of the moon, or could there be various phases of this type of work on sort of all three of those pockets? Thanks.
So we're hoping to do a small-scale test on a robotic lunar lander Eclipse program vehicle, and then also in competition to conduct tests on Artemis missions. Those haven't been selected or even fully submitted yet, but the proposals. But to address the lunar gravity, the issue is you need lunar gravity levels, and so we really need to be on the lunar surface to get long duration lunar gravity compared to Gateway or Orion tests, which would all be at 0 G.
All right, thank you very much for those questions and answers. Joining us next is Dr. Shane Hegarty, Principal Investigator for Neuronics. He's the Chief Scientific Officer and co-founder of Exenus Therapeutics, a Boston-based biotechnology company. Previously, he was a research fellow in Boston Children's Hospital and at Harvard Medical School. I will turn it over to you, Shane.
Hello. Exenus Therapeutics NASA Neuronics project on the ISS aims to improve precision neuroscience modeling and therapeutic development by leveraging microgravity conditions in space to develop a novel 3D assembloid model of the mature human brain, in which our neuron-specific gene therapy will then be tested. To do this, we are sending mature, differentiated human neurons and glia derived from human-induced pluripotent stem cells to the International Space Station, where they will be 3D self-assembled in microgravity conditions on orbit. In addition to the human brain cell types, Exenus Therapeutics is also sending a proprietary AAV gene therapy to the ISS for testing in this novel model. In recent years, a major development in neurological disorder modeling and drug discovery has been the utilization of induced pluripotent stem cells, which can be generated from the skin or blood cells of patients. These cells can be taken from any patient and then reprogrammed into becoming cell types of the brain, which have two broad classes, neurons and glia. Patient iPSCs can also be used to generate organoid models of the human brain, which are amazing models. But making organoids can be very lengthy and labor-intensive process. And in some cases, brain organoids lack the cell types and maturity needed to study particular neurological disorders. Exenus' NASA Neuronics project aims to push the boundaries of using human iPSC-derived brain cells to model diseases in space, where we can make any brain cell from any patient to model their disease. We will test whether subpopulations of human neurons and glia that are usually only studied in 2D on the ground in monolayer cultures can be rapidly assembled into a 3D model of the mature human brain on orbit. In this way, we can model the neurological disorder of an individual patient more precisely, directly studying human biology, and then testing novel precision medicines for their specific pathology. In summary, the 3D mature human brain assembloid model being developed through this ISS project could be used as a therapeutic discovery platform for testing novel precision medicines for neurological disorders. By using iPSCs from any patient, efficiently differentiating them into disease-relevant cell types on Earth, and then leveraging microgravity to rapidly assemble this combination of cell types into a 3D brain model of their disease on orbit. During this pilot project in space, Exenus Therapeutics will also aim to validate this model by testing a neuron-specific gene therapy for neurodegeneration. I'm happy to take any questions now.
Thank you. We'll now take questions for Dr. Hegarty Again, please press star 1 to be entered into the queue. And I have a question on once you get results from this experiment, what are the next steps in terms of moving forward on improving treatments for neurological disorders using this research?
If we can validate this novel model on orbit, the next steps would be to look at different patient models and to scale up this screening platform on orbit. So we've made the protocol as simple as possible to facilitate the scaling in the future. We demonstrate the utility of this system for studying human pathologies. Then we can generate the cell types from patients of interest and send them into the space where they can be rapidly 3D sample assembled into these models. Once we can study their pathologies, we can then screen novel therapeutics for these disorders.
Thank you. We'll now hear from Dr. Lasse Clausen, one of the principal investigators for the multi-needle lung mirror probe. Dr. Clausen is a professor of plasma and space physics at the University of Oslo, Norway, and has been working with the lung mirror probe for over 10 years. Dr. Clausen?
Yes, hello everybody. Thank you for having me. So I'll talk a little bit about the multi-needle lung mirror probe. So a lung mirror probe generally is an instrument that is used to characterize plasmas. So as you know, I'm sure, around the ISS there's still atmosphere. It's very thin atmosphere, but still it is there. And what's more is that the atmosphere around the ISS is not like the air that we are breathing right now. Around the ISS, it's not electrically neutral. So you have the molecules and atoms that are flying around the ISS. They have been ionized, which means they've given off an electron. And so now you have the atmosphere around the ISS being electrically conductive. And so it's in the plasma state, as we say, and we would like to characterize that plasma around the ISS. And typically you do that with Langmuir probes. That is, Mr. Langmuir invented the probe, 100 years ago, so those have been around. What makes our instrument special is the multi-needle part, which allows us to make measurements a lot quicker than is usually done. So we can do several thousand measurements per second, and that allows us to resolve the plasma at the very smallest scale. So as the ISS is zipping through the plasma environment, we can measure very fast, and then we can resolve small structures. And that has two benefits. We can, first of all, study processes on these scales, which you could not do before, so do basic plasma physics. But it also has a more applied component because it's called the ionosphere, this part of the atmosphere that's partly ionized. It's aptly called the ionosphere. And it is there between us on the ground and satellites above us. And so every signal that a satellite sends needs to go through the ionosphere as it propagates to the ground. And the ionosphere, these structures that we can study with our instrument, they can distort signals. And this is of particular interest for us for systems like GPS, these global navigation satellite systems, where you locate yourself on the surface of the planet using satellite signals, but these signals are distorted by these small-scale structures in the ionosphere. And so our instrument aims to measure these, characterize these, understand the processes that make these structures, and then eventually, hopefully, maybe we'll be able to predict them and do kind of a space weather forecast where you can say, tomorrow your signal of the GPS receiver will not be as good as today, along those lines. And that is kind of what I thought I would say about the multi-needle Langmuir probe, and I'm happy to take any questions.
Thank you. We'll now take questions for Dr. Clausen. Again, please press star 1 to be entered into the queue. And I have a question. The multi-needle Langmuir probe has flown on other platforms before. So how does the version going up on Northrop Grumman's CRS-19 compare to earlier versions, or differ from earlier versions?
Well, So it's currently in orbit on 2 satellites, a Dutch nano satellite and a Norwegian kind of backpack size satellite. And what we can do with the ISS is really exciting because it is both more flexible in terms of software, but it's also advanced in terms of hardware. So it is called a multi-needle Langmuir probe because literally it has needles, metal bits, metal cylinders, which point into the plasma and measure. And we have more of those. We have 6 instead of the usual 4 that we flew earlier, which allows us to do more sophisticated measurements, but also the flexibility that we can command the instrument ourselves. So we will have a station at Oslo University, a computer where we can command the instrument directly. And usually when your instrument is on satellites, you need to go through a whole set of, so you ask somebody nicely, can you please, run this experiment on my instrument? And then it'll go through many, many different sets of stations before the instrument is finally commanded. And here we skip all of that and we have direct access to the data and the commanding of the instrument on board the ISS, so we can do really interesting and new experiments that we couldn't do before.
Great, thank you. Finally today, we'll hear from Chisamu Yamanaka, Principal Investigator for iSpace SA. He is a Planning Section Manager at IHI Corporation and a Senior Researcher with JAXA, who has been working on iSpace SA since 2001 and hopes this project will inspire students to follow JAXA's research and presence in space. Chisamu?
Thank you. I sincerely appreciate NASA for inviting me. Good day, everyone. Today, I want to share our project's remarkable impact on the students and teachers and the outstanding findings we have discovered. First, let me share the critical concept of our project, iSpace SA. The project aims to explore the future of education. We connect schools across borders through the ISS, Japanese culture, and the internet. Also, we provide students and teachers an online system to collaborate and create wishes upon a star. Next, I want to focus on this mission. This mission will carry a single memory card of 8,000 students' wishes in 2022. The memory card will be stored in Japanese experiment module on ISS and eventually become a shooting star. In 2022, 6,000 students and teachers from 31 schools in 7 countries, the US, Australia, Germany, the UK, Spain, South Africa, and Japan collaborated and created space poem in Japanese. Space poem is a type of Japanese beautiful linked verse. Many students who speak Japanese as a second language participated, enjoying cross-cultural engagement. Now let me share the power of space poem. Students from a school in Charlotte, USA, and a school in Ehime, Japan collaborated and created an iconic space poem. It comes out shining brightly, a wishing star. Don't be defeated by the coronavirus, and don't give up hope. Students from a school in Houston, USA, and a school in Nara, Japan created a universal space poem. You are not the only one who is struggling, and I will support you. Hard time, everyone has it. These poems remind us of our shared humanity and the strength we find in unity. You can find and translate all the students' beautiful space poems on our website. Now let's discuss the impact and the findings. Since I initiated this project over the past 23 years, 70,000 students and teachers have participated. Their contributions have been compiled into anthologies featured in school textbooks and websites. These anthologies celebrate the growth and the potential of students as humans in the universe on Earth. In 2023, we received requests from 42 schools in 8 countries to continue this incredible project. Season 23 has just already begun, and we are excited to continue this journey for exploration and learning together. Finally, my deepest gratitude to NASA and JAXA for their support. Thank you for your attention. Any questions?
Thank you. We'll now take questions for Tsutomu. Again, please press *1 to be entered into the queue. And Tsutomu, I'm curious, what was your favorite part of the project and the experience of working with the students?
Thank you for asking me. My favorite part of the project is witnessing the remarkable growth and the resilience of the students I had privilege to work with. Despite the challenges they faced after the, for example, Great East Japan earthquake in 2011, do you remember? These students showed incredible progress and determination to overcome obstacles. It was inspiring to see their creativity and dedication during the collaborative creation of a space plan. Working with them was truly rewarding experience, and I'm grateful to have played a part in fostering their hope and dream for the future. I have written Japanese textbooks and books with the goal of sharing the incredible strengths of these students with people around the world. So they are available for reading on our website in the PDF format, and the AI translation is also possible. I would be delighted if you could take a look. Thank you.
Thank you. We will now take additional questions for any of our speakers. If you would like to ask one, again, please press *1 on your phone. Our first question is from Will Robinson-Smith with Spaceflight Now.
Yes, hi, thanks for taking another question. To Tsutomu, was there anything that surprised you from what the students created, or something that was particularly inspiring? If you could give a specific example, that'd be fabulous. Thank you.
Oh, thank you very much. Yes, what I was most how do you say? Every poems are extraordinary because we are very surprised that a student has a very strong motivation so they would like to be humans in the universe on Earth. So they easily take over the barriers of across borders, and they could easily be friends. So that is the most remarkable findings for us. Is this enough for you?
Yes, thank you.
Thank you.
Thank you.
Our next question is from Mark Carreau with Aviation Week and Space Technology.
Thank you, Mark Carreau, Aviation Week and Space Technology for sure. Mine's for Catherine Toon. Can you tell us the size or volume of the exploration potable water dispenser and where it will be installed on the space station? And maybe how long you hope it'll function for your assessments?
Yeah, hi. Thanks for the question. I can't, offhand right now tell you the exact volume. I will say it goes into an express rack. So if I were to be rough in my dimensions, the height, length and width, it's about 2 feet, 1 foot, and about 2.5 feet deep. It's pretty sizely, I guess, and it is relative to the same size as the current potable water dispenser. It goes into a double mid-deck locker. I think your next question I heard was how long do we hope that it'll be up there and operate for? So it's interesting for a lot of our exploration Eclipse technologies that my group funds and supports. We start off with a 3-year long objective to demonstrate the technology. But a lot of these systems that we're creating and upgrading for life support on ISS really have a goal to be up there and working as long as ISS is, funded and operating. So though our goal is 3 years, we would plan to use exploration PWD through the life of station 2030 or so.
Where will it be located?
Oh, I'm sorry. Yes, node 3.
Thank you.
All right, thank you. And thank you to our speakers and to those of you participating and listening for your interest in these important investigations that are launching aboard NASA's Northrop Grumman CRS-19 mission. You can follow all the research being conducted during Expedition 69 on the space station by visiting nasa.gov/station research news or following ISS_research on Twitter. Stay tuned to nasa.gov for regular updates in advance of the upcoming launch. We are targeting Sunday, July 30th for our pre-launch media teleconference, and our launch broadcast coverage will begin at 8 p.m. Eastern Time on Tuesday, August 1st. As a reminder, a replay of this teleconference will be made available on the NASA Videos channel on YouTube. Thank you all for joining us, and this concludes today's telecon.